In this example problem, we're going to imagine what happens when a 1.5 kilogram piece of hot iron, whose initial temperature is 525 degrees Celsius, gets dropped into 2 kilograms worth of water, which is itself initially at 15 degrees Celsius. We're going to assume that no heat is lost to surroundings when these two objects are mixed together, so that any heat that's generated will flow from one object or substance into another. If we think about what's happening here, we can imagine a hot piece of iron being dropped into cool water in a beaker like this. Our iron itself is red hot. Our water is fairly cool. No heat can escape from this water or iron to surroundings, and therefore, what we expect to happen is that over time, our iron is going to cool down and our water is going to heat up. That's because heat energy is going to be transferred from iron out into the water of the surroundings for that hot iron. That means that iron cools down or loses heat energy while water heats up or gains heat energy. Because heat has nowhere to go but water or iron, any heat energy that iron loses must be equal to any heat energy that water gains. This is the first law of thermodynamics. Energy can't be created or destroyed, it just changes forms. If we translate this word equation into a mathematical one, then we can suggest that any heat that iron loses could be represented by Q for iron itself. Since losing heat energy is associated with a negative cash flow or a loss of energy from a system, we're going to put a negative sign in front of this symbol to represent that heat is going away from iron. Iron is losing its heat energy. On the other side of this equation, we'll think about water gaining heat energy. Anytime a substance gains energy, its net cash flow of energy currency is positive. We can put a positive sign in front of the symbol on the right-hand side of this equation. From here, we know a few expressions that tell us about the quantity of heat, Q, associated with a substance. We know that Q can be related to mass and the specific heat capacity of substances, or to number of moles in the molar heat capacity. In this problem, we're given molar capacities for our iron and water. So perhaps it's best to use our molar heat capacity equation to deal with this problem. That the quantity of heat associated with a number of moles, N, a molar heat capacity, C sub M, and a change in temperature, final minus initial temperature, for a particular substance can be calculated in this way. We can plug that information over into our equation on the right-hand side. For iron, for instance, keeping that negative sign in front and replacing Q with N, C sub M, and delta T, I end up with this: number of moles of iron, the molar heat capacity of iron, and the change in temperature for iron must be equal to the number of moles of water, the molar heat capacity for water, and the change in temperature for water. I'm not explicitly carrying through that positive sign, since not having a sign there implies that this whole right-hand side of this new equation that we're developing is positive in the first place. In order to plug numbers into this equation, we need to convert 1.5 kilograms worth of iron into moles. We need to convert 2 kilograms worth of water into moles, and we can accomplish that using metric conversions and stoichiometry, like we learned earlier in this course. When we solve for number of moles of iron, we ought to get 26.9. And when we solve for number of moles of water, we ought to get 111. These two numbers can be plugged in wherever we see moles of iron or water respectively in the equation that we're building down here. We know molar heat capacities for water and for iron. We know the temperature that each one started at. The initial temperature for iron was 525 degrees Celsius, and the initial temperature for water was 15. We also know implicitly that after enough time has elapsed, our iron and water are going to thermally equilibrate, which means that they'll arrive at the same temperature because there will become a balance between the amount of heat energy that iron is giving off to water and the amount that's flowing back into iron. Over a long enough period of time, the final temperature for iron is going to become equal to or equilibrate with the final temperature for water. With all of those concepts in mind, we can solve this equation. To do so, I'm going to start plugging those numbers in wherever I see them here. On the left-hand side of this equation, we've got a negative sign that we'll keep out in front. The number of moles of iron we calculated as 26.9. The molar heat capacity of iron we were given as 25.1 joules per mole degree Celsius. And the change in temperature is our final iron's temperature minus our initial iron's temperature. We don't know what the final temperature will be quite yet, but we do know that our iron started out at 525 degrees Celsius. On the opposite side of this equation, the number of moles of water were 111. Our molar heat capacity for water were given as 75.3 joules per mole per degree Celsius. And once again, we don't know what the final temperature of water will be quite yet, but we do know that it will be the same as whatever the final temperature for iron is. So I can leave that as the same variable on this side. We know that the initial temperature for water was 15 degrees C. So now we have a single equation and one unknown. It's just that that unknown shows up on two sides of this equation's equal sign. So we're going to have to manipulate both sides of this equation in order to isolate our final temperature all by itself and solve for it. To begin, we might distribute on the left-hand side and the right-hand side by multiplying 26.9 by 25.1. That ends up with, keeping a negative sign out in front, 675.19. I'm going to drop units from here and we'll incorporate units again at the end, but notice that our units of moles are going to cancel out. And eventually, because we'll be dividing in the future, our units of joules are going to cancel out, and we'll just be left with units of degrees Celsius by the time we're done with everything here. But we'll come back to that in a little bit. When I multiplied 26.9 by 25.1, I end up with 675.19. That gets multiplied by the entire quantity final temperature minus 525, again dropping units. On the opposite side of the equation, I'm going to do just the same thing. Multiply 111 by 75.3 and eventually distribute. 111 times 75.3 gives me 8,358.3. That gets multiplied by the quantity final temperature minus 15. We're one step closer to being able to isolate this final temperature unknown by itself on one side of our equation. To do this, let's distribute the quantities on opposite sides of our equal sign, meaning multiply 675.19 times T final, then times negative 525. Do the same thing over on the other side. Multiply 8,358.3 by the quantities in parentheses. When we do this, we should end up with negative 675.19 times T final. And then because we have a negative sign right here and a negative sign right there, we'll have plus 354,475. On the opposite side of our equal sign, we'll distribute once again. We'll have 8,358.3 times T final. Notice in this case, this is a positive number. When we distribute and multiply it by negative 15, we end up with minus 125,375. Now this looks like an equation that we should be able to solve. I could add 675.19 times t final to both sides. This gets rid of the entire term on the left-hand side. Similarly, I could add 125,375 to both sides. That gets rid of the entire term on the right-hand side. And then what I'd end up with is 354,475 plus 125,375. That's 479,850 on the left. 8358.3 plus 675.19 leaves me with 9,033.5 times t final on the right-hand side. To solve this, now we just divide both sides. And we'll have to keep in mind that our units at the very end are just going to be in degrees Celsius. Remember earlier, moles and joules canceled with each other. My final answer in degrees Celsius into 3 significant digits should end up as 53.1 degrees C. That means that over a long enough period of time, our iron is going to give off heat energy to the surrounding water. Water is going to equilibrate with iron, and as they do, the final temperature that this isolated system should reach is 53.1 degrees Celsius.